Okay, we've got slides. That's good. And I have no idea how this is going to go, but let's give it a shot. Okay, so one of the things that Unix has, I think, done since the beginning rather well is to be a vehicle for creating and using languages. Some of those are mainstream programming languages. C is the obvious first of those in a sense, and C++ is the natural follow-on to that. But then there were a whole bunch of other languages which were not what you would call mainstream in the sense of I will take on any particular programming task no matter what it is, and the language will be good for it. But rather, there were a bunch of languages that in some way were smaller and more interesting. So let me give you an example of this, and I'm going to see whether this thing works. I was once quoted as saying that if I were going to be marooned on a desert island with only one programming language, it would have to be C. And I think that's probably still a correct statement. But anyway, let me give you an example where this shows up. Okay, so here's exploratory data analysis. Exploratory data analysis is actually a phrase that I think is associated with Bell Labs back from the days when John Tukey was still here as the world's premier statistician. So here's an example that came actually from one of my students at Princeton who was bad-mouthing his roommate who was a geoscientist. And the task that had been set by somebody in geoscience for these poor children was, okay, we have a whole bunch of volcanic eruptions here, and we want to find all of the ones that have magnitude greater than 6. And so the question is, how do you do this? Okay? And at least as my student badmouthed his roommate, he said the roommate was doing it by hand. Right, okay. Nobody here would do that. What you would do instead, of course, is you would write a program in your favorite programming language. Okay, so as I said, I'd been quoted as saying, gee, C would be the right language. So I decided when I heard this story, let me go and write this program in C. So I did. Here it is. It took me, no comments on style, just knock it off. It took me an embarrassingly long time to make this work. Well, first, I blew the arguments of fgetS. I've never gotten those right, Mike. It's all your fault. Because, you know, does the file source go at the beginning or at the end? Well, I got it wrong the first time. And then the question of, well, what does it return? It either returns -1 or null, and I got that wrong. So, okay. And then I have to parse the lines. They're separated, the fields are separated by tabs. And so I had to use strtoc, which has got to be the worst function ever created in the C library. And I don't know who to blame for that, although if anybody wants to raise their hands, I'll acknowledge them. I finally got that part right. And then the scanf. Well, gee, I said %d. I want to scan into %. I did get the ampersand right. Okay, got that right. But I unfortunately forgot that %d is decimal, integer that is. And so I had to say %f, but oops, I got that wrong. It has to be, because I was using doubles, it had to be LF. So because of all of this, it took me probably 20 minutes to half an hour to get this program to work. It does work. It's not robust. If somebody gave me a number that had more than 1,000 digits, it would fail. But passing over that, it actually works. And it runs pretty fast, as you can imagine. So then I rewrote it in my second favorite programming language. And as you can guess, this took me probably less than a second to write. It worked the first time. It's robust. There's nothing wrong with it at all. And so what this says is that there is a sort of trade-off here between the kinds of languages you might use and the tasks you want to do with them. And so certain tasks, C is an entirely appropriate language. I would not want to write an operating system in awk. But for other things, suitable languages are a good choice. And there's a saying here, Benjamin Whorf was a well-known linguist in the first half of the last century, and he had this wonderful phrase about language shaping the way we think and determining what we can think about. Now, he was talking about mostly the languages used by Native Americans in the Southwest, But I think it applies even more strongly to the artificial languages that we create to tell our computers what we want to do. The notation that you have at your disposal makes a lot of difference. The better it fits your model of what it is you have to do, the more likely it is you'll be able to write a program that works well, get it working fast. There's another quotation that goes along with this, which I've always been fond of, from Alan Perlis, which says that a programming language that doesn't change the way you think is not worth learning. There's probably some contrapositive which explains why I can't get into Haskell, but that's okay. Anyway, so what I wanted to talk about today briefly is little languages. That is, languages that are more like the awk end of the spectrum than the C or C++ end of the spectrum. So a little language, also sometimes called application-specific or domain-specific languages. These are languages that focus on something little. They're not trying to take on everything in the world, as I said. They're trying to take on some relatively small part of it, but by virtue of that, being able maybe to do a better job on that. They don't have to be programmable or Turing complete. In other words, you couldn't, in principle, with some of these, write an operating system. And that declarative style of language is often quite a useful thing, as we'll see. And the interesting thing, and I think this is the important thing for anybody here who actually likes to program and build tools and so on, most of these special purpose languages are comparatively small enough that you could imagine building one yourself. As opposed to, I can't imagine building even C, let alone C++ by myself, but I can imagine lots of these other things being much smaller. And so here's a list, by no means complete, but just the ones that came to mind while I was thinking about what I would say here today. Regular expressions, for example, are pervasive in Unix. I don't know whether that was Ken Thompson's influence originally. They showed up in the QED text editor that he brought with him to Multics, and then the simplification for ED in Unix. The shell itself as a programmable tool. The entire document preparation suite, which various people have worked on here, including Lorinda and Mike and John Bentley. The language development tools like Yak, Steve Johnson, wherever he went, there he is, and Lex with Mike, and Make with Stu Feldman, and awk, which we'll talk about in a bit, S, statistics, which is now best known through its clone R, and the ample modeling language that Bob Forer and Dave Gay and I did. So all of these are languages that actually let you do things more conveniently in more narrow domains. So let's actually take a look at one of these in more detail, and it's entirely appropriate because I have the perpetrators very close by. So as we looked in ancient times, how the mighty have turned gray. But anyway, so awk is a language that Al and Peter and I worked on just over 40 years ago when we were, in fact, in adjacent offices. And so somebody asked me earlier about how do you arrange to have a successful career. One thing that helps tremendously is to have super good people in the next office. So I recommend this highly to all of you. Fortunately, Bell Labs has always had a tradition of having super good people everywhere, so it's probably going to work out. Anyway, so awk is a language for pattern scanning and processing, as it says there. And it was intended for really, really simple kinds of tasks like that. Find all the places where the third field is greater than 6 is an example of that. One of the ones that we used a long time ago when cards were more prevalent was this idea of the length being greater than 80. In other words, things that wouldn't fit on a card image. Or other kinds of simple transformations like that. So that's what awk is. I'm guessing everybody here has at least heard of it. Many of you have, I hope, used it. But if not, that's okay. The basic idea of awk is something called the pattern action paradigm, and this is something that I learned from Al Aho as part of this. The idea that the structure of a pattern action program is you have a sequence of patterns, and for each pattern there's an action, and all you do is you go through the input and say, that pattern matches, let's do the corresponding action. And so it's a very, very natural way of doing certain kinds of computations, the kind of things where something comes in, gets processed, and some part of it goes back out again. The patterns can be regular expressions in awk, or they could be numeric things, or string expressions, or mix and match any way you want. And the basic loop there is in effect a triply nested loop because it goes over a list of files, and for each file goes through the lines, and then for each line it goes through the patterns. And if the pattern matches, it does it. So you can practically see how this would work and how the implementation might go. I'm not going to give you an awk syntax thing, but just a couple of very simple examples to show you some of the things that we did to try to make it easy to use, something that would make it so that the average awk program was only a line or two long. So the first example here is a pattern with no action. So what it does is to print every line that matches the pattern. And the pattern is if the number of fields on the line is greater than 0. In other words, if it's a non-blank line, by default, print it. Okay? The next one's slightly more complicated, twice as big, getting close to the biggest awk program you might reasonably want to write, in fact. And what it does is every line, that first part of it, is a action with no pattern. So it says apply on every line, and it simply increments the sum by whatever's in the first field. And then at the end, a sort of pseudo pattern, it says, well, print the resulting sum. So this just adds up all the things in the first column of a data, or first field of a set of data. And again, lots of things are happening for free there, and therefore you don't have to say anything about them. You don't have to initialize variables. The variable sum starts at 0. You don't have to specify field separation. Fields are split for you automatically. And of course, you don't have to specify anything about the input processing. And then the last one is one that Al and I could probably type blindfolded here. This is the, how do I count the frequency of words in something? And so what you do is you read each line, and for each field in the line, you increment an element of an associative array. That is an element whose value is arbitrary, typically a string, sort of like a dictionary in Python or a hash table in Perl or whatever your language might be. And then at the end, you print them out. And so a very, very simple example, but it was kind of the touchstone example for us of what you might want to be able to do very, very easily in a language like this. Okay, so that's fine. How do you build one of these things? Well, I don't know. Fortunately, I had people around me who did know. One of them was Alejo, who was the author of a famous book on compilers, the Dragon book. And I don't have the cover of the Dragon book, but one of the things here was a picture of, well, how do you do a compiler? This is a compiler, and there's a lexical part, and there's a syntactic part, and then there's generate code, and out the other end comes an executable program. Well, we didn't want to do that because compilers means you have to generate code for a particular machine. So the cheap way to do it is an interpreter, which turns out to have essentially the same picture, except the bottom part is easier. And so that's what we did. And when I say we, it's the royal we. Actually, Al provided the insight for this, and Peter did the implementation. So if it doesn't work, it was Peter's fault at that point, not mine. But we're still not home free, because how on earth do you write? Just went blank. I'll just have to look up here. Probably means I talked too long. Anyway, how do you do this? How do you build one of these things if you are not a compiler expert or a language expert or anything else? And it turns out that just about the time, a few years before this, that we had been working on this, Steve Johnson had created this wonderful program called Yak, which lets you define the grammar of a language and attach semantics to it so that you could actually figure out what the structure of programs in a language would be, and then it would do a lot of the work for you in basically creating a parser. And shortly thereafter, Mike created this program called Lex, which would look after doing the lexical analysis part of the program. So you didn't have to do that either. And that meant that all of this nice stuff about building a compiler, big parts of it had been taken care of by tools which were themselves languages. So what we have is a language that we're building or designing called awk, and it is using tools like Yak and Lex, which are languages themselves, to build things. Okay? And how do you build these things? Well, gee, you could sort of specify things just writing it out, typing a bunch of commands to the shell, but that's sort of tedious, and it gets worse as you have a more complicated build process here, because now you have to run your grammar through Yak and your lexical stuff through Lex, and then all the other stuff goes with that into a C compiler. And so you use this thing that Stu Feldman created called Make. So that's a language, a very declarative language that says, okay, here's how you create something out of its piece parts, depending on when those piece parts were last updated. Now, this was a time when machines were very, very, very slow, and so you didn't want to do any compilation that you didn't have to, and so Make was a great boon because of that. It made it so that you never had to worry about what was up to date or not. You just said Make, it did, and you were done. Okay, so far so good. So now we have this program called awk. It's defined with a parser generator like yak. It has lexical stuff done with lex. It's built with make. What do? It produces an a.out. You ship it. Well, some places ship, a.out, it ran one test case, I'm done. We decided to do a little better than that, and so we started to actually build a test harness for it. Let me give you one piece of the test harness for it. awk contains regular expressions. Thanks to Al's work on egrep, that code went straight into awk. And so how do you test regular expressions? Well, regular expressions are a language, very small language for specifying patterns of text. And so what we did was to create another language, a very, very, very focused one, that simply says, this regular expression matches this input, this input, this input does not match this input, this input. And so we have a language for specifying regular expression tests, and now we have to execute those tests. Well, what's the obvious thing to do? We will run a program over the test to create a bunch of shell commands that will then execute the tests. What language do we use to generate those sequence of tests? awk, obviously, because that's what it's good at. And so this thing creates a sequence of lines, shell commands that look exactly like this, and then those get piped into the shell, and if everything goes well, nothing is said. And if something's broken, it will complain about a particular test. And so this is one part of a very extensive test suite for awk. There's another one that's quite similar for expressions and lots of other things. But you notice how many languages are in play here? All kinds of different languages. Okay, so the thing is working, it's been shipped, it's been tested carefully, nothing can possibly go wrong, and then what you want to do is to get people to use it. That means documentation. How do you document something? Well, I just happen to have with me something you can do, right? You can write manuals, all kinds of documentation, the Unix programmer's manual that Doug worked so hard on over the years, and Andrew, somewhere here. And a sequence of tools, grep, John Bentley and I used to create graphs, went into PIC, which I had done, TBL, Mike's program, EQN, Lorinda and I did, TROF, Joe Osana, to create a finished document, book-size thing, which had the advantage that all of the programs in the book were tested automatically, so in principle, at least, there were no typographical errors induced in that as we went along. So what you can see there is a boatload of languages playing well together. And I think that this is one of the things that Unix in the early days made it very, very feasible for us to do. And it was a lot of fun. And I think it was a bunch of virtuous cycles, or circles, depending on how your imagery, where an idea in one thing would make something else better, and then you could use that to feed back subsequently. Now, it's absolutely true. There's no programming language that does everything for all people. And Alan Perlis, again, quoting, there will always be things we wish to say in our programs that in all known languages can only be said poorly. So think about that when you're designing languages. But in the meantime,
yeah, Bjarne, invite you up on stage. Yeah.
So I'm, in some sense, one generation after Brian and the people you saw earlier. And so I feel a little bit young here. And I'm going to talk about the big languages in this game, C and C++. And they were among the languages done around here, actually one building two mostly. And this was a wonderful place to work, and you learned a lot. Purpose of the exercise is to actually build things people can use. When we talk about languages, at least when somebody talks about languages, they may forget that the purpose of the exercise is to provide useful tools. It's not just to write really nice academic papers and see how clever you can be in two-column format. So this is what keeps me going. There's a lot of good stuff directly and indirectly in this slide, and maybe I should just show this slide and walk off stage. But of course, I'm not going to do that. This is the way that, from the C++ perspective, that's the way I see the world. There's two things that really needs to be done, which is we need to use hardware well. Every cycle, every byte, people have been telling me ever since the 80s that efficiency doesn't matter and hardware is infinitely cheap and things like that. I don't quite believe it. Somebody's business has to be to use the hardware well. Today that also means batteries, and it means latencies over networks and things like that. On the other hand, down there at that level, the world is rather unpleasant. It's cold, it's unforgiving. So we work on abstraction. And you see the top line there, special purpose abstraction, general purpose abstraction. And when I came to Bell Labs, got a job, was told to do something interesting, looked at the walls around the doors and realized that something interesting around here is not what it is in many other places. I have to do something interesting. So I joined some of the abstraction stuff with some of the efficiency stuff. Brian and Dennis was down the hall, so for low-level stuff I chose C, great language for that. And I built on Simula with better static type checking and very flexible abstraction mechanisms. It wasn't cheap, so I had to make it cheap because I wanted to do systems work. I actually wanted to build a distributed system, and if I hadn't been distracted into language design, maybe we would have done something interesting there. Basically, out of these two languages, C and C++, a lot of the modern programming world is there. I'm not going to talk about the whole thing, but notice the side branch over to Java and C# and such. There's a lot. And there has been some progress. There's two pictures there that illustrate it. For the younger people in the audience, I can point out that they are to scale, and that little cable down the bottom is how you connect it to the wall, and it doesn't actually work unless you're connected to the wall. And we started with a language with Kernighan C when I was here and learned it, and it looked like the top there. That's how you sort a sequence of integers. And today we've reached something where we can sort just about anything by saying sort that something, sort A. And so we can sort integers, we can sort strings, C-style strings, and it'll all work out fine. Yeah, and the modern code runs faster too. So there's progress. It may not be the most dramatic progress, but we're dealing with the lower things. Now, one of the reasons, in my opinion, that C and C++ succeeded was that Dennis had a really good idea, which was to have a simple model of what the hardware was. There's a series of objects, there's operations there, and we can compose things out of things like that. This is really simple. Hardware was never that simple. There was registers and all kinds of complicated stuff, and today we have FPGAs and GPUs and all of that. But what you have on this slide is basically a treaty between the compiler writers, the optimizer writers, and the machine architects. And this has stood us in good stead for about 40 years, and every year people have told us it's too simple. We have to do something else. Maybe one day we'll have to do something else, but this actually is the basis of a lot of stuff that has worked. And as hardware has changed, as languages have changed, if you really want to build reliable, efficient, economical systems, you end up with something like that. Another quote from Dennis: C is a strongly typed, weakly checked language. And I sort of took it as a challenge. I would like it to be at least as strongly typed, but less weakly checked. And so we started out with something where you could say that square root and qsort each took arguments maybe, and then you could call it and you have to get everything right. And the first thing I did when I tried to build C++ was to look at that and says, that's just not good enough. And everybody happened to agree, it's just what do you do about it? And my department head then, Sandy Fraser, told me, well, just go and do it right. And so I added arguments checking and conversion, so the square root of 2 no longer crashed because 2 wasn't a double, because the compiler now knew that it was a double and knew how to convert things. And while I was at it, I changed the syntax for declarations so that they were more regular and easier to deal with. And the only thing we had in those days to check that a program compiled different parts, actually that the parts matched, was a program called lint that people tended to forget to run. So I managed to cheat the linker into checking these things, and so at least we couldn't run stuff that didn't match. So it starts with that. The major features of C++ was classes and templates. We wanted user-defined types, we wanted some form of resource management, and we also got object-oriented programming from Simula, whereas templates comes in when you want to parameterize things with types or numbers, and you get generic types and generic operations known as algorithms. So let me just show how those two things work out. So we want to raise the level of abstraction from the raw memory. The raw memory, there's a pointer, there's something over there, and there's that many of them. That's a representation down there at the bottom, there. And we want to raise it to something that where you construct and initialize, and you can copy and move the specific access, and you've got a destructor that cleans up the mess afterwards. That's the start of C++. It's in the first week or two. And basically, class means user-defined type. I borrowed the name from the Simula guys. So if you ever write in a programming language that calls a type a class, you can thank Christian Nygaard. And this is parameterized on the element type, so that's all nice and reasonably elegant. And it's also efficient. It doesn't have any fat thrown on it here. So what you can do is that you can deal with your resource management by having types. You initialize them with values. There's a vector of double, a vector of strings, a vector of file streams. File streams are file descriptors with some buffers associated with it. Or we can have a vector of lists of threads. And you can start them out empty and fill them up. The point here is that what I showed on the previous slide, that is constructors that creates things, destructors that clean up things, works recursively. And so at the end of the block here, whatever still is owned by these types will be cleaned up by the destructors. And that's the basic idea here. I sometimes have to point out that some resources are not memory, which means that if you think a garbage collector will help you, you're wrong. It will forget about the locks you have grabbed, the file handles you have taken, the threads that are still running. This stuff actually does it right. The other thing that we needed for generalization was some way of dealing with generic types. There's people who sort of think that was invented around sort of much later, but actually I wrote a paper in '81 that said you needed the object-oriented stuff and you needed the generic stuff. And I conjectured that you could do generic stuff with macros, and I was very wrong. but sometimes it's a good idea to have the right problem, even if you have the wrong solution. So we want to parameterize things being types, functions, things like that. We want containers types to be, we can parameterize an algorithm with what kind of containers it'll take. We can parameterize the element types of those containers, and we can parameterize with the operations we do. That's all very general. It's sort of generic in 3 dimensions, and examples are threads, locks, dates, and operations like accumulate, sort, merge, find, if, and such that work over the containers there. And basically the aims of this stuff was to be extremely general and flexible. My statement at the time was I wanted something that could do things I couldn't imagine, because I have a healthy respect for my limitation in that respect. I wanted 0 overhead because really I wanted to be able to afford things like that vector in direct competition with a CRA. And so we couldn't afford to have a lot of indirections in place. And then on top of that, I wanted well-specified interfaces on these generic things. Unfortunately, nobody knew how to do that at the time, not all 3, so I had to pick the 2 first, and the C++ community suffered rather badly for the next 20 years. But basically, for generic programming, I can say I want to sort anything that is sortable. It's a sortable range. It says in the ISO definition, the ISO standard, what that means. And so, is a string something that's sortable? Yes, it is. It's a range. It has random access, and the elements have less than. That's a definition. An array, yeah, I can do it. So basically, I would like to make generic programming just like ordinary programming. There's nothing particular complicated about that. And we have to go a little bit further. Most of the time, we want to do operations. So I want to find something in some sequence. And the only thing I need to know about the sequence is that I can traverse it. None of this random access stuff. We just want to read one element at a time and apply a predicate that says whether we found what we were looking for. So I can take a list of integers and look for something that's greater than 7, or a vector of strings where the operation I specify is that it has some vowels. This is reasonably simple and close to optimally efficient. There's no spurious indirections there. It maps straight down to that memory model I showed Dennis's idea. We can say, how do we define interfaces in this world? We do it by compile time predicates, that is, functions returning booleans that we run in the compiler. And so an input range is a range that where the way you look into the range is an input iterator, means you can read from it once at a time. A range is something with a beginning and an end. That's about it. For the sortable range, I need access. It says so in the standard, so I specify it like that. This is, again, not rocket science. It is actually first-order predicate logic, so it's very general, and it's very simple to write. This is something that has been running for a while, but will be official in C++20 next year. C++ is controlled by a rather large and unmanageable standards committee. You can see a few of them there. When the committee is in session, there can be this many people in it. It's really hard to get things done, but C++20 is going to be great. This stuff that started here over in Building 2 is still going on, and it's not just languages, of course, but a lot of it is going on still, and we're nowhere near finished. And so I'll say a word about languages. No one language is ideal for everything and everybody. There's just so many language fanatics, language devotees that think they've got the solution. they may very well have the solution to something. I mean, a lot of us think that we can do well in certain areas, but the idea that there's a single language for everything is, I think, odd. Like, I want mathematical precision for anybody that builds engineering kind of things for me. I don't want the planes to crash. I don't want the net to go down, etc. On the other hand, ease of use is for most people, and it is really hard to convince individuals and educational establishment that this distinction is important. And a language is simply a center of a tools environment. It's not everything. You never write a program just in a language. You write it in a tool chain and a tool environment. So the ideal representation is something of a language of code is something that's easy to manipulate and strongly typed, which is one thing that we got wrong with C and C++ because the source text is the definition, and that is unmanageable. It's sometimes even unreadable. Anyway, we can do much better. So anybody who tells you we're at the end of development of science or whatever it is, don't believe it. We can do much, much better. In my particular world, which is not uncommon, I think, people want a smaller, simpler language. Of course they do. The languages are big and complicated, just about all of them. And in addition to having a smaller, simpler language, they want about 2 more features. Each of you want 1 or 2 features, and they are not the same. And furthermore, everybody wants full backwards compatibility, because don't break my code while you're fixing it and simplifying and adding to it. And by the way, people use different implementations, different tool chains, so what they want to be compatible with is not the same. This is hard. And of course, we want to interoperate with other languages and systems. This is hard. I mean, language design for a general purpose language is close to impossible. And by the way, this is where every general purpose language ends if it is successful. The only way not to fall into this trap is to fail. And we don't want to fail. So basically, that was what I wanted to say. Thank you.
All right, hello everyone. My name is Tom van Cutsem, and I'm a department head here in Bell Labs and a researcher. And if Bjarne was feeling young, I don't know really what to say, other than that it's hugely humbling and a great honor to present here for you today. So the question that I would like to talk with you about today is whether in the future we will pair program with an AI. Now, let me maybe start with a different question, a more general question. What is it that makes software developers more productive? Now, I found this definition of what a programmer is on the web. A programmer is an organism that converts caffeine into code. So maybe the answer to my question is coffee, and I'm sure many of you will agree. But more seriously, what makes software developers more productive is their tools. And in fact, the ACM every year awards a Software Systems Award to a tool that has had a big impact on developer productivity. In fact, Unix won that first award in the year of 1983. And so I'm going to take a slightly broader perspective than purely programming languages. So think about tools as things like Make, things like compiler suites, things like integrated development environments, and so on. And so from that perspective, I'm going to talk about a few big trends in the software industry and how they might influence how we're going to build tools for languages in the future. Now, the first trend that I'm going to talk about is one that I'm sure all of you have already heard of. It's the rise of machine learning. Now, if we put that in a historical perspective, so when computers first appeared on the scene, we used them for numeric computing. And of course, the pioneering language to do that was Fortran. Now, a few decades later, we figured out we could use computers for totally different tasks than just simulations. So we had algorithmic computing, and we had other languages like ALGOL and Lisp that were really pioneering there. And Algol is sometimes said it's sort of the most influential language you've never heard about. It went on to have a huge influence on BCPL and then later C. Now, fast forward to today, we find ourselves in what some people call the cognitive computing era, where we figured out how we can make computers become good at recognition, classification tasks, prediction tasks, and so on. And if you look at sort of the pioneering systems, the state-of-the-art systems in that space, it's interesting to observe that they are not sort of entirely new programming languages. They're rather what some people call embedded domain-specific languages. For instance, for deep learning, there's Theano, Torch, TensorFlow. These are all libraries that are implemented in a host language, in this case, all of them in Python, which appears to be sort of the dominant language for machine learning today. And that's actually a topic that's also going to come back in the talk by Lieven and Lode. Now, machine learning is all about prediction. In particular, when you're working with textual data, one very important task is for a machine to try and predict the next word in a sentence. For instance, if I give you the sentence, I thought I would arrive on time, but I ended up 5 minutes, and then I ask you, to fill in the blanks, you probably have some idea of what words would fit that context. Now, if you train a machine to become good at this task, what you get is the tools that we're all familiar with today, like the auto-completion tools in our chat clients and our email clients. Interestingly, you can apply this same game to code. So if I give you this line of C code, and I ask you to fill in the blanks, what should go there? plus I. I thought everyone was going to go for I++, but okay. ++I is certainly also a good fit. And of course, we don't really know if this is the good answer. We would maybe need more context, but certainly it's a very high probability answer. And actually, more formally, when you're trying to play this guessing game, what you're really trying to do is to estimate a probability distribution. And it's a conditional distribution of what is the chance that I'm going to see this token given that I've seen a bunch of prior tokens. And the state-of-the-art tools that we have today to estimate those probability distributions are neural networks, and more commonly, recurrent neural networks. So these are machines or contraptions where you feed in the tokens, and it goes through a whole bunch of computations, matrix multiplications. And what the thing spits out is a whole probability distribution over all the possible tokens in your language or in your corpus. And it turns out that code is even more predictable than natural language. And recent research confirms this. So actually what's here on this chart is sort of the entropy of trying to predict the next token for a certain corpus. And so the lower the entropy, the more predictable the corpus is. And what you can see here is for C and Clojure, Haskell, Java, Ruby, it's consistently lower, the entropy is consistently lower than for English, German, and Spanish natural languages. So that's interesting. And so if you have enough code to train on, and if you have enough compute power to sustain a very large neural network, then you can build tools like this. So this is from a company called Tab9, and they built an auto-completion tool. So every time sort of developer hits tab, there's this sort of window that pops up, and the suggestions that are in that window to complete the code were learned by a machine learning algorithm, by just reading millions of lines of C++ code. Okay? Now, interestingly, so the company did not just do this for C++. They actually also did it for, I think, 6 or 7 different programming languages. And this is the same tool now operating on a piece of Python code. And this is an interesting observation. It's a sort of general trend where, previously we would have implemented, let's say, code auto-completion tools by manually inputting the syntax of Python or C++ and to a certain extent the semantics. These tools learn about the syntax of a language and to a lesser extent the semantics of a language purely from data.
They can't use it unless it's in DI.
Sure. So, second trend I would like to talk about with you today is what I would call the Cambrian explosion of software. So today there's this huge diversity of languages, tools, frameworks, components that developers can choose from to build systems. And just one data point, if you take the top 3 programming languages most widely used today, they are in fact JavaScript, Java, and Python. And for each of those languages, there is a package repository where developers can publish ready-to-reuse modules or libraries. And in fact, for JavaScript, its package manager is called NPM. earlier this year, it crossed the threshold of 1 million packages being available in that repository. And it's growing at a rate of over 750 new packages being published there every single day. That's not updates to existing packages, that's entirely new packages. And so this poses sort of a new problem. Like, how do we help developers find the most appropriate library to get their job done? What we need is a map. Now, not a map in the traditional sense, like I'm depicting a map of Java, the Indonesian island. We actually want a map of Java, the software ecosystem. And this is from our own research here. So what you see here, this point cloud, every dot is an open source Java project, and we've labeled some of the better known Apache open source projects. And what we did here is we trained a machine learning model using techniques similar to what I've talked about before. And the model tries to predict which libraries would tend to be used together in a source file. And if you do that on a large enough amount of data, then the machine actually learns, or the machine learning algorithm learns which software libraries are sort of semantically similar or contextually similar. And again, this is a generic technique. So we didn't just do this for Java. We did it for different programming languages. And for each of these languages, you get a map that you can then explore, and you can actually see what is this language being used for, what are different sort of niche ecosystems. And if you zoom in like on very specific libraries, for instance, if you would zoom in on NumPy, NumPy is a very popular numeric computing library for Python. It actually sort of sustains the whole machine learning stack on Python these days. And so if you look at sort of what the model has learned, it learned to place NumPy very close to scikit-learn, SciPy, Matplotlib, Pandas, and so on. Now, these names may not mean much to some of you, but if you tell this to a Python data scientist, he will immediately go, yeah, that makes total sense. So this is interesting, but of course, the question is, how does this actually sort of help developers become more productive? So we don't just train these models, we translate the models into actionable tools. So what you see on this chart is a screenshot of Microsoft Visual Studio Code. It's a pretty modern integrated development environment. And so the developer is writing code, and they can summon our extension called Code Compass. So when you open it up, Code Compass will actually start reading the developer's code and figure out what libraries they are using. And then together with the map that it has built of the open source ecosystem, it can figure out what other libraries would be helpful to that developer given his particular software project. Now, I would argue, if you take just a little step back, that this is already an example of an AI pair programmer. We have the developer writing their code, and they're summoning a tool that is built using AI that has access to the developer's code, but also to the sort of the knowledge latent in the large amount of open source software. So coming back to my original question, will we ever pair program with an AI? I hope I've convinced you that the answer to that is certainly yes. And at Bell Labs, we are actually building sort of this next generation of AI pair programmers. And with that, I'd like to end my talk, and thank you for listening.
So by now, I think it's clear that many of the Unix concepts that we discussed this morning are still relevant today. And I'd even dare to say that today, they have become more relevant than ever. And what we want to do here is give you a quick peek under the hood of the Bell Labs Worldwide Streams technology, a research project still in the making, still a work in progress, but that's leveraging and extending some key Unix concepts as we speak, and we will try to convince you or to argue that we are, as a matter of fact, inventing Unix pipes for the 21st century. Now, worldwide streams as a technology, it is really very relevant in a context where you need to make sense of a lot of data. Data that is continuously streamed from our environment, data, video, whatever streams, and that is so massive that you really have to select the relevant pieces out of this abundance of available data, and that's a quite hard task. Data that is ephemeral and that needs to be processed really in a timely manner before the information just disappears. And it is quite a challenging task, and if you as a developer would want to create such applications, there are a few challenges to tackle. So one of the challenges is clearly, as Tom already mentioned, a Cambrian explosion of available frameworks, available libraries for you to choose from. So it is about complexity, but it's also a huge integration effort. Even if you pick the proper libraries, you still remain with a significant integration effort. And the second challenge is about functionality. Over the last decades, as you all know, software software has evolved from quite monolithically designed applications or software services to really increasingly fine-grained microservices. Microservices that are all addressable, connectable via the network. So the amount of available API endpoints for you to develop against is simply unsurmountable. It's really huge. So again, complexity and integration effort. And then as Marcus already introduced, so finally, led by a wave of latency-sensitive and bandwidth-sensitive applications, software has finally managed to escape the confines of the centralized data center. We see now that it's a generic requirement from software services to be spread. The compute needs to be spread across the central cloud, edge cloud, premises, and even on the device. So again, you as a developer, you will need to deal with the challenge of distributing your compute of your application across this distributed compute fabric. Again, complexity and integration effort. Now in Bell Labs, we have been working for quite some years now on this worldwide streams technology, a platform technology that is designed to deal with this fragmentation of frameworks, functionality, and also the location. So it allows you as a developer to easily, quote unquote, create applications that tap into all these live streams of data and video, assign analysis or processing functions, and then do this in a monolithical way, but still deploy in a distributed fashion. Now, of course, a lot of bold claims. So in the true Unix style and philosophy, we have to think, what are the languages, or what is the language we would need to create this kind of applications, to wire them up, to orchestrate them? How do we do the plumbing across this distributed fabric? And also, how can, at all times, we keep a systems view across these distributed and highly complex applications?
Thank you. So 4 years ago, when Bell Labs started the Worldwide Streams research, we created a new programming language called Extreme to address the upcoming needs Lieven just mentioned. And in this talk, I will position Extreme as the Unix pipe for the 21st century. Doug McEnroy once said, once Unix pipes were introduced around the 70s, it became the philosophy that everybody started putting forth. I mean, it allowed many developers to write programs that do one thing and do it well. The pipe mechanism then enabled the composition of these programs for building new applications. And this really meant that you could stick together applications end to end, such that the data flows from one program into another. So you no longer had to worry about compiling or linking these programs together or how the communication was handled. You could simply use them without knowing their internal details and regardless in which programming language they were programmed in. Now, what if we could leverage these ideas and apply them in a new context to accommodate the future needs? Now, I personally see the world as one big reactive system, and it would be a dream to tap into any remote information stream and use that information to improve our daily lives. Now, unfortunately, simply grabbing a video stream on my laptop for actually extracting meaningful content would already consume multiple terabytes of data every month. This clearly doesn't scale well. And so in order to optimize for bandwidth, we should distribute the logic of an application across a distributed network of processing machines, ranging from the tiniest IoT sensor to the largest compute clouds. And this is exactly what we aim for in our Extreme language. So Extreme, at its core, leverages the Unix pipe concept to easily compose software. Now, the way this works is that each function call you see here is actually a proxy for certain functionality. And it uses a specification rather than an implementation. So in this example, we have written an application that taps into a video stream and then filters the foreground motion before sending it to an output channel, which could be a web page, for example. Now, each module listed here was implemented in C separately, but composed in a high-level scripting language. And by doing this, we have now exposed the communication patterns of our application to a platform. And this is the key to unlock wide area distributed deployment, meaning you can write a single application, but leverage whatever machine is best positioned to actually run the software. And you can then build an infinite amount of optimizers that target bandwidth, latency, fault tolerance, GDPR compliance, and so on. I mean, anything your application prefers or requires. Now, there are two main strategies to define a new programming language. You can write an external domain-specific language that uses its own syntax rules, a parser, and so on. Or you could host your constructs on top of an existing general-purpose language. That approach is commonly called an internal DSL. Now, although external DSLs have clearly a very strong tradition in the Unix community, we note that internal DSLs are very common nowadays, with prominent examples such as TensorFlow, which builds upon Python. You have Spark that extends Scala, and so on. And this, I think, is mainly because internal DSLs allows developers to use the tools and syntax they are already familiar with. Additionally, it also allows us to grow and benefit along from evolutions in the host language. Therefore, we opted to design Extreme as an internal DSL on top of JavaScript. And JavaScript today is a very popular agile scripting language, and it allows us to tap into one of the widest developer communities out there. And under the name of ECMAScript, JavaScript has evolved quite drastically in recent years and provides many of the new language features you would expect to see in any modern programming language. For example, one of the currently proposed extensions to JavaScript is the pipeline operator. And once included in an upcoming standard, we can immediately benefit from that. Now, another recent addition to the thriving ecosystem of JavaScript is something called TypeScript. So TypeScript is a superset of JavaScript where you can optionally type your code to ensure certain properties are adhered to at compile time. And I would argue that gradual typing, it's strong typing, but weakly checked, is probably one of the core features that's required to easily compose software in today's fast-changing software world. Now, Extreme leverages this gradual typing to its fullest and really can inform developers when a certain composition cannot be done without adding a particular transformation. Now, remember, these transformations, they do not have to be written in JavaScript. As I mentioned before, Extreme uses a software specification as the proxy for an implementation. And this plays really nicely along with using the best tool or programming language to implement the job. For example, using the latest C++ features to implement a novel video encoder. Now, when distributing code across multiple machines, it is really important to ship the required content and dependencies to correctly execute that program. And we have developed and open-sourced a new JavaScript serialization module that allows us to transmit all required configuration over the network. Now, I'd like to conclude that we don't have a clear end goal for our project. I think we have to continue improving upon the Extreme language as well as the Worldwide Streams platform such that more people can reap the benefits of programming in a centralized way without needing to be aware that your program might just be using the battery of your neighbor. And I'd argue what we really want is to simply make mass communication of information more efficient. Thank you.